Welcome back. Last episode, a matrix learned to act on a single vector, and the answer was a combination of the matrix's columns. Today, one matrix acts on another. Now, adding matrices was easy. You add the entries, so a natural guess is that multiplying means multiplying the entries. That guess is wrong, and understanding why it is wrong is the most important idea in the course after the vector itself. Matrix multiplication is built so that the product of two matrices corresponds to doing one transformation after another. The product A times B is the single matrix that first applies B, then applies A. Multiplication is composition. Once you hold that idea, every rule we meet today becomes inevitable rather than arbitrary. We will see the row times column recipe and the column recipe, learn why order matters, but grouping does not, find the identity and the powers of a matrix, and finish with block multiplication, the trick that powers fast numerical computing. Let's build it. Here is the working definition, the one you compute with. Suppose A is m by n and B is n by p. Then the product A times B is m by p, and its entry in row I, column j, is the ith row of A dotted with the jth column of B. In other words, slide the ith row of A across the jth column of B, multiply the matching numbers pairwise, and add them up. Watch the 2 by 2 example. To get the top left entry of the product, take the first row of the left matrix, 1 and 2, and dot it with the first column of the right matrix, 5 and 7, 1 times 5 plus 2 times 7 is 19. The top right entry uses the first row against the second column, 1 times 6 plus 2 times 8 is 22. Work down to fill in 43 and 50. Notice the result is not the entrywise product of the two matrices. It mixes rows and columns together. This recipe is correct and mechanical, but it does not yet tell you why multiplication is defined this strange way. For that, we need the idea of composition. Now the real reason. Every matrix is a linear map, a transformation of vectors. Suppose you want to transform a vector x by b first and then by a. You compute b times x, and then you feed that result into a, getting a applied to the quantity b times x. Doing two transformations in a row is called composition. Here's the question that defines the product. Is there a single matrix C that achieves both steps at once, so that C times x always equals A applied to B times x? Yes, and that matrix is exactly the product A times B. So A times B times x equals A applied to B times x. The order reads right to left, like nested functions. B acts first because it is closest to the vector, then A, and this forces the recipe. The jth column of the product is the product applied to the j8th basis vector, which is A applied to the j8th column of B. Work that out in coordinates and you get exactly rows of A dotted with columns of B. The entry recipe is a consequence. Composition is the meaning. There is a second, cleaner way to see the product, and it ties straight back to last episode. Write B as a row of columns, the first column, the second column, and so on. Then the product A times B is formed column by column. Its first column is A applied to B's first column. Its second column is A applied to B's second column, and so on. Each column of the answer is just a matrix vector product. Exactly the A times x we mastered last time. Run once for every column of B. And remember what A times x is, a combination of the columns of A. So every column of the product lives in the span of A's columns. This column view is often the fastest way to multiply by hand, and conceptually it is the most honest. A times B is nothing more than A acting, in turn, on each column of B. Hold both pictures, rows dotted with columns for the entries, and A acting on whole columns for the structure. They are the same operation, two angles. Before the rules, the bookkeeping, the same conformability rule from last episode, now for two matrices. Write A as m by n and B as n by p side by side. The inner dimensions, the two n's, must match, and when they do, they cancel, leaving the outer dimensions m and p as the shape of the product. So a 2 by 3 times a 3 by 4 gives a 2 by 4. But a 3 by 2 times a 3 by 2 is undefined because the inner numbers, 2 and 3, disagree. This isn't an arbitrary restriction. Composition only makes sense when the output of B lands in the space that A expects as input. B sends vectors into Rn, A must accept vectors from Rn. If those spaces don't match, you cannot chain the maps and there is no product. Here is a striking consequence. It is entirely possible for A times B to be defined while B times A is not, or for both to be defined but come out different sizes. That already hints at the next rule, that order matters in a way it never did for ordinary numbers. Here is the rule that trips up everyone coming from ordinary arithmetic. With numbers, 3 times 5 equals 5 times 3. With matrices, A times B usually does not equal B times A. Order matters. Look at the counterexample. Let A have a single 1 in the top right corner, and let B have a single 1 in the bottom left corner. Multiply A times B and you get a 1 in the top left, zeros elsewhere. Multiply B times A and you get a 1 in the bottom right instead. Same two matrices, genuinely different products. Why should this be? Because composition is order sensitive. Think of transformations. Rotating the plane and then projecting onto an axis is not the same as projecting first and then rotating. The order in which you apply the maps changes the outcome. When it happens that A times B does equal B times A, we say the two matrices commute, and that is a special, noteworthy situation, not the default. Treat A times B and B times A as different objects unless you have a reason to believe otherwise. The order is lost, but plenty stays nice. First, associativity. When you multiply three matrices, it does not matter how you group them. A times B, that whole thing times C, equals A times the quantity B times C. You may regroup freely, you just may not reorder. The reason is again composition. Chaining functions is associative. Do H, then G, then F, and the grouping of those steps never changes the net effect. Second, the identity. The identity matrix is the do-nothing map, so the identity times A is A, and A times the identity is A. It is the number one of matrix multiplication. Third, powers. For a square matrix, A squared means A times A cubed means 3 copies multiplied, and in general, A to the k means applying the transformation k times in a row. By convention, A to the 0 is the identity, the empty composition that does nothing. The distributive laws survive too. A times a sum is the sum of the products. So we keep associativity, identity, powers, and distribution. We lose only commutativity, and we lose it because composition genuinely depends on order. Last new idea, block multiplication. You can chop a big matrix into rectangular submatrices, called blocks, and then multiply the two matrices as if the blocks themselves were single numbers. With one caveat, you must keep the order, because matrix products don't commute. So the top left block of the answer is the first block row of A combined with the first block column of B, exactly mirroring the row times. Column recipe, except now the entries are whole submatrices that you multiply and add as matrices. The only requirement is that the blocks be conformable. The column sizes of A's blocks must match the row sizes of B's blocks, so each little product is defined. We have actually been using a special case all along. The column view of the product is just block multiplication where B's blocks are single columns. Block multiplication is not only elegant, it is the secret behind fast numerical linear algebra. Splitting matrices into cache-sized blocks is how the high-performance libraries behind every scientific computation and every GPU keep the processor fed and fast. Here is composition as a picture, the whole episode in one frame. On the left, a simple shape sits on a grid, say the unit square with one corner marked. The first arrow, labeled B, carries it to the middle grid, where B has transformed the square, perhaps shearing it. The second arrow, labeled A, carries that to the right grid, where A has acted as well, perhaps rotating it. 2 arrows, 2 steps, first B, then A. Now look at the single curved arrow sweeping underneath, straight from the left grid to the right grid, labeled A times B. That one matrix does both steps at once. That is exactly what the product means. The single transformation equivalent to doing B and then A. And the picture makes non-commutativity obvious. If you reversed the steps, applying A first and then B, the shape would visit a different middle grid, and almost certainly land somewhere else. The order of the arrows is the order of the matrices, and swapping them changes the destination. Let's see non-commutativity directly. 2 panels, each starting from the same unit square, marked asymmetrically so we can read its orientation. In the left panel, we apply A times B, shear first, then rotate. The square is sheared into a slanted shape, then that slanted shape is rotated, landing in one final bold position. In the right panel, we apply B times A, rotate first, then shear. The square is turned, and then that turned square is sheared, landing in a clearly different final position. Between the two results sits a bold not equal sign. Same 2 transformations, a shear and a rotation, applied in opposite orders, and the square ends up in 2 different places. This is what A times B, not equaling B times A, looks like in space. There is nothing paradoxical about it once you think in transformations. The order in which you do things to an object usually matters in everyday life too. Matrix algebra simply records that fact faithfully. Let's multiply 2 matrices both ways and watch them agree. Take A with first row 1, 2, and second row 0, 1, and B with first row 3, 1, and second row 2, 4. First, the entry recipe. The top left entry is the first row of A dotted with the first column of B, 1 times 3 plus 2 times 2, which is 7. The top right is the first row of A with the second column of B, 1 times 1 plus 2 times 4, which is 9. The bottom left is the second row of A with the first column of B, 0 times 3 plus 1 times 2, which is 2. The bottom right, 0 times 1 plus 1 times 4, which is 4. So A times B has first row 7, 9, and second row 2, 4. Now the column check. A applied to B's first column, 3, 2, gives 7, 2. That is the first column of the answer. A applied to B's second column, 1, 4, gives 9, 4, the second column. The two recipes produce the very same matrix, exactly as the theory promised. Now let's confirm non-commutativity with real numbers, using the same A and B. We already found A times B has first row 7, 9, and second row 2, 4. Let's compute B times A in the other order. Top left, first row of B, 3, 1, dotted with first column of A, 1, 0, that is 3 times 1 plus 1 times 0, which is 3. Top right, 3, 1 dotted with 2, 1, 3 times 2 plus 1 times 1, which is 7. Bottom left, second row of B, 2, 4 dotted with 1, 0, that is 2. Bottom right, 2, 4 dotted with 2, 1, 2 times 2 plus 4 times 1, which is 8. So B times A has first row 3, 7, and second row 2, 8. Compare. A times B is 7, 9 over 2, 4. B times A is 3, 7 over 2, 8. Completely different matrices from the same two factors. This is not a quirk of these numbers, it is the normal state of affairs. Always respect the order. Last example, powers, and the identity as their anchor. Take A with first row 1, 1, and second row 0, 1. Geometrically, this is a shear. Its slides point sideways in proportion to their height. Let's compute its powers. A squared is A times A. Working it out, the top right entry becomes 2 while the rest stays put, so A squared has first row 1, 2, and second row 0, 1. A cubed pushes the top right to 3. The pattern is clear. A to the k has the number k in the top right corner, 1's on the diagonal, 0 below. And that makes perfect sense as composition. Shearing k times in a row shears you k times as far. Powers are nothing but repeating the transformation. And the base case fits the convention. A to the 0 is the identity, the do-nothing map, the shear applied 0 times. The identity in turn satisfies the identity times A equals A and A times the identity equals A, sitting in the powers like one sits among the integers. A short history that explains the strange definition. In the early 1800s, mathematicians like Augustin Louis Cauchy were composing substitutions of variables, replacing one set of variables by linear combinations of another, then doing it again. Chaining those substitutions is what the matrix product secretly records. In 1858, Arthur Cayley made it official. He defined the matrix product precisely so that multiplying two matrices matches composing the corresponding linear substitutions. The definition was reverse-engineered from composition, which is why it looks odd until you know its purpose. Cayley's name also attaches to a gem, the Cayley-Hamilton theorem, which says every square matrix satisfies its own characteristic equation, a complete fusion of algebra and transformation we will reach in the eigenvalue episodes. And block thinking turned out to be deep. In 1969, Volcker-Strawson showed you can multiply 2 by 2 blocks with only 7 small products instead of 8, making large matrix multiplication asymptotically faster. The product, born from composition, took on a life of its own. Let's recap. Matrix multiplication has an entry recipe, the entry of A times B in row I, column J is the ith row of A dotted with the jth column of B, and the sizes follow the inner match outer survive rule. But the meaning behind the recipe is composition. A times B applied to x equals A applied to B times x, so the product does B first and then A. The column view says each column of A times B is A applied to the matching column of B. From composition, the rules follow. Multiplication is not commutative. A times B usually differs from B times A. It is associative. You can regroup A times B times C freely. The identity is the do-nothing map, so the identity times A and A times the identity both give A. Powers of a square matrix mean repeating the transformation. And block multiplication lets us multiply conformable partitions as if the blocks were numbers, keeping the order. Next episode, the inverse, the transformation that undoes A, the matrix that multiplies A back down to the identity. Today we defined matrix multiplication, and the key was that it is composition of transformations. The product A times B is the single matrix that first applies B and then applies A, do B, then do A. From that one idea, every rule follows. The entry recipe says the entry of A times B in row I, column J, is the ith row of A dotted with the jth column of B. The column recipe says each column of A times B is A applied to the matching column of B. For these to be defined, the dimensions must be conformable. The number of columns of A must equal the number of rows of B. Because composition cares about order, matrix multiplication is not commutative. A times B usually does not equal B times A, but composition is associative, so A times B times C equals A times the quantity B times C, and grouping never matters. The identity matrix is the do-nothing transformation, so the identity times A equals A, and A times the identity equals A. Powers of a square matrix mean repeating the transformation A squared is A times A, and block multiplication lets us multiply matrices in chunks as long as the blocks are conformable. Next episode, the inverse, the transformation that undoes A. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.